Hello, hello, hello. Ready to tackle Advent of Code Day 9. Turn clock actually on. It's on. I'm on. Let's do this. Disk map. Disk. Oh boy, we've got a warning. Okay. Here's input. Dense format represent layers of files of free space. 1, 2, 3, 4, 5. One block. Two of free, free block, four of free. Okay, so it's alternating size free, size free, size. Three 9 block files with no free space. Oh, there it is. Size free, size free, size. Okay. Move files one block at a time from the end of the disk to the leftmost free space block until there are no gaps. For 1, 2, 3, 4, 5, the process looks like this. Oh, you can just chop them up? That feels illegal. Okay, I can already see some efficiencies from if you know there are three free spaces, just grab the next three. Okay, I can see some stacking stuff. Add up the result, multiplying each of these blocks with the ID it contains. Okay, so it's get the thing, sort the thing, generate the checksum, give checksum. Okay, what's my checksum? This number. Cool. Okay, let's. First, I'm just going to do it as strings, so I'm going to be very bad. Then I'll guess I'll think about the efficient way. So const memory equals. I'll just be super bad. Say it's really bad. Um, oof. I'm trying to think of what I think of optimization ways. I should not be optimizing prematurely. I'm trying to keep like track of the free spaces and be like, oh hey, do things with them. Gonna do it. Free index used memory, and then it's free free memory. At this point, you just make it a set. That's going to make iteration a little hard. So let's go back to making it a list. So for console, well, it's for let 0 I less than data. Actually, I have to look at the visualization again. Okay, I should look at 1, 2, 3, 4, 5. No, I have no checksum for this. That sucks. So it's 1, 2 of free, 3. Okay, so as I go through these, it'll determine which is which. Okay, so const is free or use equals 0. So it's console log I is free or use. So let's see. So 0 is, let's just go for is used. So 0, a 1 block file, 2 blocks of free space. Okay, so let memory I equals 0. Then we increment it by whatever we got. So memory I plus equal size, and our size equals data I. Okay, I like that. And I don't want to do this. Okay, well, I don't know why you're not liking that. Oh, because you're not numbers. I'll fix that. Boop. I don't want to increment. I want to for loop that many times so I can fill in those slots of things. So for let m 0 m less than size m plus plus. Again, the least efficient way of doing this. So I'm going to do this plus equal plus plus. But before we do that, we have to set is used memory or free memory. It'll be, what is it? Memory I? Memory I I guess I'm setting it equal to what I'm finding. It's an ID number. So the disk 301. Oh, so it's my index. So that's my ID. Okay, well, hey, let's just go for that. That feels too confusing. Let's not go for that. Yeah, any TypeScript, everyone's angry. Did I generate the data structure I was looking for? 11 has 1, 4. That feels wrong. Oh, wait a minute. This isn't. Yeah. So 2 zeros, and then we have threes. So it's 2, 2, 2, 5, 6, 7. Then we have 3, 3. Then we have 3 more again. What's this 4 doing? What'd you do? Why? What are you in here for? That ain't right. Yeah, I feel like I have definitely tackled this in the wrong way. 2, 3, 4, 8, 11. Yeah, I definitely feel like I've tackled this the wrong way. Okay. 2, 3, 4, 8, 9, 10. 2, 3, 4, 8, 9, 10. So this is properly doing the thing. So what would be my approach here? I would go toward use memory and be like, hey, you, 41, you need to move to the current free memory position. And then I remove that from the first free memory. Feels like what I'm doing here. Feels like I've done it in the worst possible way. Perhaps I just need to generate this visualization to make build me confidence. Should I do it or go for it? Let's go for it. What's the worst gonna happen? So while free memory, well, there are free memory, so use the least efficient way of doing this. Break, do not kill my computer. Then what we're going to do is get the last used and the first free. So cost first free, object.keys, free. Yeah, again, least efficient. Cost last used equals object.keys, used memory at -1. It's there, promise you. And I think we just move the index to there, okay? Because they're breaking these blocks up. They don't really care about them. So free memory first free equals used memory last used, and then we do some deletions. You can't spell the word delete. Used memory last used. Delete. Do the same for free memory. Well, free memory. Did I just invert this? I did. Oh no. So used memory first free becomes free memory last used. Okay, so let's see. So we have a 2 slot. I'm going to fill that with whatever's in 41 slot. So use memory first free. Nothing's in there. And then you tell me something. Right, we didn't do this right. I do need to set the 2 slot into whatever is currently used over there. There we go. And then I need to delete it from there. So the first free, and then I just should delete it from first free. Free memory. There we go. I think this is what it's supposed to be. And yeah, they are. They have made me mad enough. I will fill you all. You're good. Be chill. Okay, now we need to look at used memory, free memory. Hit that autocomplete one. Okay, so we had it. Yep. 48, 41 had the 18, and now the 18 is here. The free memory is not a 2, and if the 18 is not on 48, what was it? 41. Okay, this is doing its job. I have to do the checksum bit thing now, right? So, multiply each of the block's positions, the file ID it contains. The leftmost block is in position 0. Well, I know that. It can't contain free space. The whole thing is that you get no free space. 0 times 0, 1 times 0, 2 times 9. Oh, this is index. Oh, I thought we were going to do something else. Okay, that makes it easier, I suppose. Let's trash some comments. Let this go, which should result in free memory being empty and used memory being all the keys from 0 to... Hey, you didn't do it all because there was no free memory up to that point, I bet. Right? You used... Yeah, your free memory never went up to 36. It went to 35. Oh. Okay, so I have to get the last key. So while this is happening... Okay, so it's another while loop, basically. While last key in used memory not equal... Is that what we want to do? I feel like that's what we want to do. I'm gonna do that. Well, the last key is not equal to the length of keys, keep moving it to the front. While object.keys, use memory at, oh, not flat, -1, not equal to object.keys, use memory dot let that I'm worried about an off by 1 here. We're going to do that, put a break in here, not eat my computer. Then we're going to do the thing where we have, well, we basically need to get the next free slot, which we don't have available. Okay, I think my free memory calculation needs to bump it up. Yeah, if there was just more free memory, I wouldn't be needing to do all this stuff. Yeah, so if my free memory just went up to, oh, there is no free memory up here. That's why. Okay, so if I just set free memory last key up to the thing, but then it would cause this to go further, which there might not be any. I think this approach I'm going down here is the right one. They just set all the used memory to its index. But if there are 2 free ones, then they would need to be like swapping. They wouldn't be going in sequentially where they are. Okay, I just need to populate n new frees per how many are here? No. Okay, I just need to calculate the next free slot. It's gonna be expensive, it's gonna be ugly, but we gotta do it. 4 let I equal 0, I less than object.keys, use memory.length, I plus plus. And if used memory, or if I in, except we're going for the inverse, so if it's not in, let found equals -1, found equals I. Boom, we found it. Now you need to do the swap. So cost last used. I think it's the exact same thing up here we're doing. So it's first free, just to keep naming consistent. Boom, and instead of touching free memory, we just juggle with ourselves and we get rid of that. Did it do the thing? Show yourself. I just broke it. Great. Oh, hey, there's a -1 in here. Um, let's not do that. Because that's never going to be equal because strings and all that. Put that back. Okay, seems to be running 0 to 27. We made it. Check sometime. Looks like they just multiply the index by the thing. So 4 let I 0. I listen object dot keys use memory dot length I plus plus. Yeah, I'm already seeing so much better ways I could have done this. Checksum equals 0. Return checksum. Let's do this. I times the number at it, right? And then just sum them all up. So checksum plus equal I times use memory I. 3856 is not 1928. I was about to be like, that's awfully suspicious. I'm gonna go for it. Oh, where's my input? I never grabbed it. Big line. 9.8 kilobytes. Oh boy. Hey computer, you wanna try that one? Oh yeah, I can hear fans going burr. So yeah, the least efficient approach. Who knew? It not efficient. Do you wanna start doing something? Okay, I'm curious how I doubled it. Some of these 1928. Position, multiply the file ID number 0099856. When did they get into sixes? This isn't what I got. That's not what I got. I got a bunch of teens. Yeah. 0018. Oh, I've literally doubled it somewhere. Hey, where did I do that? 0024. So what am I putting in here? Oh, right. Because the ID doesn't count the free. So I'm technically supposed to be incrementing by 2. Right? So it's fill in that many and then fill in that many free. Okay. Can I just say divide by 2? Alright, it's going to make the free memory look all weird, but their values don't matter. So use that matters. 0, 1, 2. Okay, that's good. I guess we'll do is use and data or just a bunch of ones because free memory doesn't matter. So it gets that working. The efficiency is a trash, so I'm gonna stop quality, uncomment that, try and target that with the old terminal. Let's see if we can brute force. We're not gonna brute force nothing with that going on. That's just processing. Ooh, okay, so that we're gonna hit a lot of memory. We are building a lot of memory here. I just realized. Yikes! 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 Okay, let me see free memory. What do I need here? Let's start cleaning this up. It's 0, so it's always a 0 thing. So this is technically just an array we're doing. So let's do conditional if is used else free memory dot push memory I. That's all that really matters about it in this equation. Yes, it's used memory I. Let's use memory I. Add all my symbols back. Computer finish. Computer not finish. Okay. And then while free memory length, we can also free memory dot reverse, allowing me to do free memory dot hop. Gives you the last, right? Get the last. There we go. Don't worry, it's real. And then delete, which that already did that, so you don't need to delete. Okay, that makes that one a lot less painful. This one's still gonna be a chuggy one, but let's see if I can get Wall B back on it. Okay, still working. I had high hopes. Okay, so this is still not the most efficient. So we have two bad things in here. Object keys and see, this is the last one. I have all these object keys. All these object keys. Yeah, I have so many object keys. Can I just target them? I do deletions. So it is the last of it though. So cost keys. So we can reduce a lot of this calculation. Do keys. So we delete that. Use keys at. That's just straight up a pop. Boom, which means we don't need to do the deletion. It's running. We love it. I broke it. We don't love it. We do need to do the deletion. I lied. Don't worry about it. Why are you lying? Oh, because yeah, and they're fine. So I got the not triple equals. Wake up, TypeScript, you're cool. I don't want to keep calculating the first freaking free one. I want to start from the last first free one. So let's move that up. And then we'll start I at first free. Good, you're reusing where you last gave up at. Okay, you're not doing that. You're still looking at the last one, which it's not the most expensive operation. Last used, use keys, pop. Let's do another use keys. We're adding new ones to it, however. I think it's working for us. Let's go for it. What's the worst that could happen? That's the worst that could happen. I wish you need to do a reset on this. The values just shift. Nope. Go back. Stop doing the thing. Oh wait, let's go. Let's do it further. Let's drop the delete. No. Bad mistakes. Went too far. Okay, this is a lot of optimizations. Did you finally run? You didn't. Okay. Well, yeah, give up. I got you some better code. Okay, so you're gonna go, and then I'm gonna go for the next layer of optimization here. I'm trying to think what we're really talking about here, data structure wise. What we need to do is we need to identify gaps of free memory and then pull values from the end of this until we reach that gap and then set all of those. We're not doing array operations. What is... I must have chosen the least optimal way of doing this, honestly. Yeah, I just went least optimal. I mean, I also don't think this is taking the most of my time. I'm pretty sure it's down here. So let's see what we have here. So if we just log all the free, then yeah, we'll track that down. And then if we just log these two, we can identify which of the one is the problematic. And yeah, let's stop this. Let's hit you on it. Oh, yeah, I got rid of it. What helped turn that back on? It's the free. Yeah, there's just so much free memory. Huh. Honestly, that's not a lot of free memory. We're chugging through it right now. Okay, I'm trying to think of. Obviously, if we're hitting this, then we're hitting the free memory at the end of used memory, because this is going around pretty quick. So yeah, both of them are unoptimized. How do I optimize this one though? So if we're looking at it, basically we have a bunch of sequential blocks over here. We want them all to be over here and reverse, but we want them to be moved one at a time, right? So like if we have 7 ones here, then this one goes, like these two move it over, but this one wouldn't be able to roll over, right? So like it does still need to be identify free blocks, identify blocks you can put them in. And then, oh geez, 95,000. You gotta move it down 30 freaking thousand. Oof. Okay, yeah, I think that's where my time sink is. So it's still the same problem. It's just my data structure shifted a bit. So how did I lose track? Because first example, this isn't the one I'm actually having. Okay, so if we target, there we go. So we had used memory all the way up to 41, free memory up to 35. The end of this, we had no more free memory, and our used was still up to 35. So 26 is how much we were able to use. Because everything else got sent back. Even the 35 eventually came back. Yeah, I'm definitely using that. Hey, that's a big number. I'm gonna take that. Bingo. Hey, brute force. There's a lot more contiguous free space. No kidding. Fragmentation, great. Moving whole files instead? What? Oh, if anything, this might be easier because this bruteness was what was killing me. Okay, let's try this out. I think I see it. I just need to probably restructure my data to be honestly. Is it the same example? The first example. Okay, take first example. Coming on down here. 2858. Let's do this. Okay. So we have the freeze, but we can only move from blocks. Oh, and we just try and we go through all of the blocks and we're like, hey, can you move to the free, people? Okay, so for every free space, we identify the first block of data from the end that is of that size, that is not before the free space, and we just drop it in. Why don't the 8s go here? Oh, it just did just not fully show it. No span to the left of the file is large enough. File does not move. Wait, why'd the 2 go there? Oh yeah, you were able to move. Okay, but you didn't take the two first. You took the rightmost one first. Okay. So I'm seeing this. I don't think my structure of arrays and objects is really going to survive this, to be honest. I mean, just looking at this, what the heck is free mem? So, like, 0, I can see 2, 3, 4, it's there, but okay, so I go through free memory, I identify a continuous sequence of things, and I'm like, okay, find me a used memory batch from the end, go through the keys in reverse that are the same. I could use this. I fear that this thing is already so inefficient, it's just going to eat me alive, but let's do this. I am reversing it for pop efficiency. So it's pop, pop, pop until it's not the same, and then put it back. Okay, so while for memory length, it's going to be like const block of free mem equals here. Well, first it's the free memory dot what the heck dot pop. Did I get an import? I did get an import. Get the heck out of here. Oh, free memory dot pop. It's the real. Believe me. Basically, if it's the same as -1, so if free memory free, well, I just say that at -1 equals block of free memory. And what do I want to say at this? Did I say at the end? Yeah, I'll say at the end. Well, it just needs to be the last one, contiguous one. So I really need the start and the end, so I can get a size. Let block start equals free memory dot pop. Let end equals free memory. Well, it's gonna be block start. And then we keep looking till we can get one. So let's just put a break here. Save my computer. While false, it will be block end equals free memory. Import the thing. Go down to the one I want. Dot pop. Alright, so while free memory at is a difference of 1, basically. And so free memory at -1 -1 -1 triple equals block start. And this will be enough for me. I'm just possibly undefined. Don't worry about it. Why is computer angry? Hey, you want to run anytime soon? I know all this code is gone, but it should be expected things to be things. Yeah, show something. Okay, let's stop running the real one. Are we running the real one up here? Is that what's... Nope, we're not. Hello? Okay, invalid syntax. I get it. I get it. You're not even running down there. Okay, finally. Get rid of that. Get rid of that. Block start 2. Block end 3. They're supposed to keep going. So it's 4 -1 equals block end. There you go. 2 to 4. We finally got your continuous thing. Let's assume, life goes on. Just keep giving me more ends and ends. So 8 to 10, 12 to 14, 18 to 18, 21, 6, 31, 35. Okay, I'm not sure what's supposed to do all these ones. Feels like I'm getting in kind of a lock here where it's like, okay, I've looked at all the ones. I can't find any ones to slide. Okay, I think that will work actually. So we have block start, we have block end. It's block size equals block end minus block start. I think we're gonna get twos, twos, and zeros. So that's not true. I mean, it's true, but it's not true. Three threes and ones is what I'm looking for. Okay, so we have these. Now we need to just go from the other end of, hey, used fellas, what are your block sizes? And I just need to find all of them. Yeah, this calculation on the free side does make sense because it was 3, it becomes 1. And I believe this is somewhat incremental. We're not searching. The searching I'm about to do on the use side, though, this is going to be expensive. Because we're going through all the keys in reverse, keeping track of the ones that are all the same. I mean, we stop when we hit the block end or whatever, but still ain't free. Okay, let's put a break here. Break. Or so const use keys equals object keys used memory. Let's hit you with the reverse. Well, hold on. We need to look for any block that will fit. Is that true? Yeah, any block that will fit, not the perfectly sized block. So if we find a block that is of size, then we take it. We're win. Okay. We'll use block start. And then that's just going to be the first key we find, right? So that'll be used keys 0, use block end 0. And we're just going to go through all of them. So do we need the indexes here? Let's keep them. No, we don't need them. Let's go with the first one, of course. If use block end, hold on. Show me the block. These are the indexes, not the values of the things. Dang it. Okay, and also the trick is that they do need to be contiguous, which I don't think we'll find a universe in which they aren't. So we're lucky there. So we just need to keep tracking down. 6, 7, 8, 9. How are you two all contiguous? I guess there's 0 free space between y'all. Yeah, that's a possible thing. Okay, so we just need to be like, hey, just keep pulling ones out that are the same. Once you differ, you a failure. So it's T, really. Cost block equals. That's kind of the thing we need. The start and the end. We also need the block itself. So we do need this. But then we compare with what that evaluates to. So block equals used keys. Key if block not triple equals used block end, but not that. Used keys, use block end, and congratulations. Used block end, just set to block. Else, oh no, we found a failure. So use block start, use block end, and then we'll need to set that to use block start and end equal the one we just found. Okay, now we got actually some undefined in here, which is making it a little scary. We start at 41, we end at undefined. That's illegal. That's supposed to be a string there. What are you doing? What is going on? Oh, you can't do that. It's use memory. Okay, a little better. That's not possible. Oh, that's the number, right? No, hold on. You equal the key, not that one. Okay, so 40 to 41, 39, 36, 34, 32, 30. So I'm seeing ranges here. 11, 11. Okay, I need to actually see what y'all are working with. So show me used memory, used block start. Show me what memory. So 9, 8, 7, 6. Okay, it's the numbers. You should see 4 8s. So 9, 8, 7, 6. That is a 4. I should see 3 7s. 4, 3, 2. Okay, yeah, this is working. So I'm finding them. So if the start of this, well, basically I can't look in the past. That's one thing. And second is I need to immediately find the right sized. So start is here, end is here. Let's imagine I'm here. If my end is less than my start, that's gross. So we don't need to worry about this. Use block size equals use block end minus, and what did I do up there? Use block start plus 1. I don't think math is gonna like this because strings. Ooh. Alright, my ends and my starts are technically the other way around. There we go, it's a little better. And minus operator works on strings because there's nothing else you can do to them. Don't we love it? Okay, so once we do the thing, before we reset the universe, we see if this is good enough. So if the one I have is something or something to the one I need, I don't like used. The free block start, I guess. Free block end. I still don't, this verbiage still doesn't map in my brain, but it's enough. Let's see. Brain is not fully tracking on this one. So if the new size is less than or equal to the size I need, here we go. If used block size less than or equal to the size I need, then put them in there. So that's for range of start to end. We'll set all the starts to nothing and set all the ends to one I just found, and then I might have some new free blocks for you. Then once this happens, break up the party, which kills this loop and just kills that loop also. Okay, good. You're a number. You're a number. Why are you angry? Oh. Right, so you have this, you're good. Still hope you're not on the left side of the thing you're going to, but haven't read that condition yet. So we found you, you can fit. We want to fit you in our place. So it's basically for range free block start to math dot max of whichever the block size it is. So for let b equals free block start, b less than or equal to math dot min, because it might be the smaller one, used block size free block. Well, it's used. That's all we literally have. We're not doing the other one. There's no point in going the other one. B++, and then we'll be setting it to the thing, and so use memory B equals whatever we found in the thing. Use memory use block start. We did it. Now let's get rid of all our other stuff. I think I can do that right here. No, let's do that in a second loop. That's dangerous doing it in that loop. For all of those, let's call it, because the end is technically less than the beginning. And they're numbers. Well, they're strings, but they're numbers. They're keys. So this to this. Use memory B. Well, delete. There you go. You freed it up. Now we don't have the left thing going on. I don't know that. I don't think we're doing that no more. Yeah, man, that's exactly what we wanted to see. Yeah, there might not be things in there. We're supposed to do something if there's something not there. The block contains free space. Skip it. I got you. If equals undefined, well, it's not equal undefined, then we do our job. Okay, great. Now our numbers are all wrong. Part 2, 2858. We haven't gotten there yet. There were quite a few off. Okay. So what could be happening is that things are going more left than the free space they're looking to go. Let's just look at the user memory. Let's get rid of that break, maybe. Nope. Okay, let's look at our user memory. Draw my mental map of it. 0, 1, 2, 3, 4. But you didn't do nothing. You did absolutely nothing. What? Do I still have a break somewhere? So all free memory should have been consumed. Make sure did that happen? Stupid import. Okay, so all free memory got consumed. What did you do with it? Look at all these gaps. It didn't even fill in the first one. You do a lot of iteration here. They're all 9s. They're all 41s. Oh, this looks horrible. What happened? What happened? Okay, we need to start looking at more things again. So yeah, from 2 to 4, you got 3 slots of memory. 2, 3, 4. Fill them in. And you got 9. You got 2 slots of memory. Fill them in. Why don't you run this line? Oh, size. Oops. Do some pluses here for you. Okay, you're working. Now you're too much. 0, 9, 1, 9. 0, 9. Okay, you only had 2 9s. Where did you get the third one? Okay, yeah, the 4. You never filled in the 4. You were supposed to fill in the 4 with the 2. Not just leave it out there. Why'd you give up? Oh, it's totally still a free memory. So I popped it all off, but I didn't consume it all. Right. So, if there's any left over, I need to put it back. So the diff, memory back equals free block size minus used block size. So I need to put one memory back. So I need to start at the end and do that many times. Or let b equals It's really complicated. Free block end be less than put, well, free block end plus put free memory back, b plus plus. I should see, yeah, at least that one. So let's put it back. Free memory dot push b. I think all my math is juggling right. We'll see about it. B has any. Figure it out, your math. Okay, numbers got bigger. Did my 2 at least end up there? 5, 6, 7, 1. Oh, oh no. Oh no. Oh no. That's not right. Yes. Okay, so it was working before I did this. This is the problem. If I put free memory back, I need to put 1 memory back. Or 0 memory or 2 memory back, right? It's however many I'm not fitting in. So put memory back B 2, 4, 11. So 10, 11, then 14, 15. There's a lot of 2's in here. Let me look at these and together. Oh, what am I pushing back? I'm pushing back the B itself. Is that what I want to push back? Let's see. Don't lob it, log it. Yeah, so I want to put 1 back, so I'm putting back the 4. I want to put 2 back, so I'm putting back the 2 and the 11. Okay, I need to see which one we're targeting. Start end size, right? So free block end, I guess, is my identifier. So yeah, I'm at 4. I'm putting 10 and 11 back. When you put 11 and 10 back, though, 15 and 14 needs to be. It's wrong. They're wrong. That's why it's all broken. So this is a reverse array I need it to be. So what do I do? Do I start up here? So greater than or equal to free block end. Then I decrement. Is that the thing? That do it? Can you show me my logs? Okay, I think I just killed it. Please stop. Okay. So it is this and it is that, and you are greater than or equal to that, and you are decrementing. You should eventually run back into that, even if this is a 0. Dang, I've infinite looped it. What have I done? I'm decrementing it. Okay, I went for the fancy, be cool. We'll just eat all my memory. Those logs back. I need to see things. Putting back. Congratulations, you're making an array. Putting back and then putting back dot reverse and then free memory dot push. All of what you're putting back. There you go. It's the least efficient thing in the universe. Wait, did that reverse happen? Yeah, it's supposed to be largest, smallest. Okay, yeah, I think that is doing its job. Number not numbering though. 9, 9. So we have 3 9s. We're supposed to have a 2. Where do we get the 1? 0, 0, 0, 1, 2, 3, 4. 0, 1, 2, 3. Where you get the third 9 from? You ain't got 3 9s. It's something up here that's wrong now. So it's where you start to how much you got. How many 9s do you got? You got 2 9s. How many times do you run? This isn't really helping that much. Well, you're running 2, 3, and 4. No, can't do that. Oh, is this a -1 thing? Well, 2 is also too few. How did I get there? Okay, let's log all the things. Okay, so it's where you are, where you need to be. Right, you're at 2. You're doing 3. 2 and 3. Those are the two nines. You did it. You modified your user's memory. What happened? The two nines are there. What are you two doing here? You're supposed to be gone. Oh, that happens next. Do you do that? You don't. Well, you do, but you don't get rid of all of them. Eh. Okay, now it's doing it. Okay, I'm liking it. Let's hope and pray. Better, I guess. Whew. Now the 2 doesn't make it in. The 2's all the way up in 35 by the 8s. What are you doing up there? Okay, that's the left then right then thing. Right. So I need to do that logic of, hey, you're on the left of me. Stop looking. So if key. So if I'm looking to fill something 2 and 4, 0, 1, 2, 3, 4, and you look at a key that is 4 or less. Okay, so you know what? Do I always need to do this? Let's just make my life easier. If key less than or equal to free block and continue. Just well done, continue. Break. Give up. You're not gonna find anything. Please stop looking. It's getting better. Okay, my 2 got in. Then I have 3 1s, 3 7s, 4 3 5s. How many 4s were that? Yeah. So 2 1 7 4, 2 1 7 4, 3 5 6 8. 3 5 6 8. Okay, so the order is correct. Is my spacing correct? So I have a after the 7 and after the 4, I have one missing slot. After the 7, good. After the 4, good. After the 3 is 4. 18, 19, 20, 21, good. After the 5 is 1. 26, good. And after the 6 is 1, 2, 3, 4, 5. 6, so that's 5. And after the 8, you have 2, but those are outside of the universe. What's wrong with my checksum calculation now? Am I not doing the right thing with the blanks? So I'm skipping them. Attempt to move each file exactly once in order of decreasing file ID number. Starting with the file list. That's not right to left. That's not right to left. Okay, let me look at this checksum calculation. If a block contains free space, skip it instead. Free space means this thing is undefined. When I get rid of this, I get Batman. 1928, 1136. 0, 1, 2, 3, 4, 5, 6, 7, blah, 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 blah. Blank. What am I supposed to do? Okay, is this supposed to be the example I'm following? It is. 2858 These are the proper orders. This is what I expect. Let's build a thing, I guess. So toString let tr equals this. Well, it's like this for let I 0, I less than object.keys, use memory at -1, the last one basically. Convert you to a number, I guess. Plus plus str plus equal, use memory I, or a dot. Didn't need to console log it, but I am. That appears nearly correct. What happened to the 8s? I lost an 8. Someone doing some choppy. 3 1s, 3 7s, 2 4s, 3 3s, 4 5s, 4 6s, 3 8s. Did I just not go all the way? Okay, I just didn't go all the way. So this is hilarious. My memory is correct. I can't generate a checksum for the life of me. This is great. Is I supposed to be the ith block, not the ith? Well, checksum calculation, they haven't mentioned any changes to checksum calculations. Add up the result of multiplying each of the positions with the file ID it contains. Yeah, the file ID it contains is just its number. I'm putting those back in the slots. Zero zero 2 9 4 2. Hey, where'd the rest of them go? Oh, hey, that's not how you iterate over the thing. I literally just learned this. It was me. I was the fool. Are we going fast enough? 25 is not equal to 28. Okay, are we hitting them all? We are hitting them all. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Skip it. Yep. So better 25, 46. Now what's wrong? Okay, let me do a direct comparison. No, just this one. Oh, thank you. It's identical minus those 2 free spaces at the end, but they make a 0 impact. I mean, let me copy this one here too, just double blind. Well, I had a space. I'm not calculating this darn checksum properly. 2858. That's what you say, huh? 2546 is what I'm getting. The example checksum would be this number. So the index I used was 0, 1, 2, 3, 4. It feels like that might be different now. Each of the block's position, file ID number it contains. The leftmost block is in position. Block contains free space, skip it instead. By skip it instead, does it mean like keep my previous I? So let me see. Let position equals 0. Then we'll say position always go up. And then it's position times. I don't want position only go up in these circumstances. No, that's even less numbers. Yeah, because our left number goes up less. That makes complete sense. Yeah, now we have a higher multiple on the left. This is good. But not good enough. Is it 0 both of these? No, that would just give us lower numbers. So the string is correct. Resulting file checksum. Resulting file system checksum. Okay, so let's make the crazy assumption. Maybe I'm wrong. I mean, we know I'm wrong somehow. That's not the crazy part. Maybe there's something, for example, I am getting wrong that I'm not getting wrong in the real one. That's totally what happens sometimes. So let's just see what happens here. Okay, it's running. Let's get the terminal on it too, just for good measure. And yeah, that one's gonna go. A lot of searching, to be honest. A lot of double searching for all of this work, unfortunately. Very inefficient. Let's get Wally off of it. I am not necessarily seeing it. I might just call that a break until I spontaneously think of something and then come back with it. Because it makes me feel like I don't know how to calculate the checksum. Despite that basically not changing, not looking like I'm doing what I'm supposed to be doing. Yep, nothing's striking me, so I will return. There's a number in my terminal. Never mind. Returned I have. And here I am to come up with a working part 2 for Advent of Code Day 9. So, last we left off, this technically works for the example, but of course, it doesn't work for the real one, and when it does run for the real one, it takes half an eternity. So I talked about, as I was implementing this, how inefficient it was, and there has to be a better way. I think going for that better way would be the move. And then it would start to make some semblance of sense. Now, unfortunately, I think the more efficient way of this is taking it on my TL draw. Like remembering them as chunks instead of splitting them out into individuals. So right now, in memory, these are all just individual things. They know what their like ideas or whatever, but they're not associated with each other. And that is what's making this painfully difficult. Because this goes through here, and it's like, okay, let's see how much of the block we can put in. Let's put the block in. If the block's too small, block's too small. And then it does that, but then it moves characters one at a time. I think if you move them in blocks, like in full chunks, get the wrong one. If you move them in full chunks, that is the efficiency gain we're looking for. Means I need to store them in full chunks. So kind of the same structure I'm going for, used and free, but going to try and make it chunk based instead of individual based. And we're going to also attempt to make a lot of this searching down here not a problem. So we do keys reverse, we do all this searching, we try to find a thing, and then we find a thing with the right size, and we do a lot of searching logic. And that's just looking at this block, being like, oh, woe is me. Is there anyone available who can fill it? And we basically look at every single thing. If we just looked straight for the things that were of the correct size, that would work. And I think that's doable, because if we look here, everything, it's kind of implicit, but it's not obvious. Everything's a single digit. You can't have a block of more than 9 long, which means there are only, like, if there's a gap size of 3, well, there's a gap size of 1, 2, 3, 4, 5, 6, 7, 8, or 9, which means you can make a direct lookup to find, instead of searching, hey, any gap sizes of 3, 2, or 1 out there. And then I would get the 9s. And then once I'm here, I'm like, hey, any gap sizes of 1 out there? And I'll go straight to the 2 for this one. Hey, anyone of a size 3, 2, or 1? Instantly find this one. Instead of all that searching. Well, I find the 7s actually, because I'm searching in this direction, which is a fun part of the implementation. But those two optimizations are my hope. It's going to get me fast enough to run through this. I haven't even honestly thought of how that would apply to the first solve one. I guess I can make it in which the blocks I record are of different sizes. Or they're all of size 1, rather. Yeah, I'm not going to worry about that refactor till I actually have it working. Okay, so we're going to want at least these 2. And I think we're going to go with my bucketing approach. So, record. And these are actually numbers. Right, instead of being straight numbers, they are an array of numbers, because these are the locations of free memory. And what do I want for this? I want where. So I need the location and how big. So I need the size. So I'll just take this, location, number, size, number. And let's not super optimize it. Let's not make that an array, because it's going to be harder to work with. Okay, so we have that. We're going to want to do some of this. So we have our memory index. This is our position in the world. We go through it, check if it's used. We grab the size. Yes. Yeah, and instead of doing this, we fill in each one. It's going to be kind of 2 universes. Let's start with the simplest one. Is used. I can see that one in my head. And then we're just going to set the position. Well, we're going to set something to this object. So const object equals location. I think that's memory I, and then our size, which is our size. Okay. And then use memory. This is the ID. Like, I want it to be this thing. So that's my index. But on my index, my position ID, which is my index divided by 2, because of the weird logic. Let's see if that turns out to be what I want. It's not on. okay, we have everything's at a location is 0. That ain't right. It would help if we incremented this at all. Okay, 0, 2, 4, 6, 10, 12. That's not right because location changes not by 2, but by the size. Okay, so at 0 we have 2 zeros. And at 5 we have 3 ones. 0, 1, 2, 3, 4. Okay. And then at 5, 6, 7, 8, 9, 10, 11, we have 1, 2. 11, we have 1, 2. Okay, this is something. It's doing something. Now we have no free memory though. So need our else. Which do I want? So the trick is I want this to be by size because this is part of the lookup. So I want to be like, okay, here are where all the frees of this size exist. So since it's size based, that's my key. It's not size and free memory. Oh, this stupid autocomplete again. Then free memory size equal empty array. So I have the sizes, and then in those will be the position of each of those sizes. So free memory push the position, which is memory well, the size. Okay, let's see if that looks like what I want. Okay, so at 0, we don't care if your size is 0. That's let's not look at that. Else if size. Okay, so we have a bunch of 1 slots, and then we have a couple of 3 slots. So 2, 8, and 12 are my 3 slots. 2, 8, 12. Then we have a bunch of 1 slots. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So we have these. So yeah, we've changed our data structure slightly. Hopefully this is a little bit more obvious of like as we go through these, we'll be able to see like, okay, hey, we're looking to find kind of gaps to fill these free memories with these. Right, because we're going from the largest ones here, well, from the end, or the largest, whatever, tomato, tomato, and we're like, okay, we're looking at you, number 9, you're at 40, that doesn't really matter, you have a size of 2. Are there any gaps that we can fit you into? So we're looking for gaps of 2 and higher. I don't think the order, what order would we prefer them in? We prefer them in the index left to right, so that'd be some filtering, some sorting. Okay, there's some stuff in there for finding the available gaps. Once we find one, we take one. We still have to do this logic of somewhere around here. I think this of, hey, we can't place you for to the left of you. And then, yeah, we place you, then we handle the remaining, I think. Okay, so we have all this. This is good. I'm looking at this. 2, 8, and 12. This order is ascending. Which one of these would I pull off first? I try to pull off the first one in here, which would be a splice. I don't like that. So we want this sorted the other way. Let's just do it out here. Array of let's just have them sorted descendingly. There we go. So that way I'll just pop off, kind of, so kind of should be treating it like a heap, but not using one, just using sort to get these out here. I'll pop them off, do what I want, and then the trick is that there might be some leftover, so I'll have to add something back to it, which would positionally be close, but it might not be, so I'll probably have to do another sort to re-heapify the thing, even though I'm not using heap. Okay, I like it. So let's stop ideating and start going for it. So we want to do this for all of them, I suppose. But we want to do it in the order of highest to lowest. So it'd really be all the keys of used memory, but high to low. I do not want to put a while loop in here because could, but it'd just be decrementing from 9 to whatever. But 9 might not be in there. It could be different numbers. I think it's just a reverse for loop of. Yeah, let's just go for it. If it doesn't exist, doesn't exist. So for 9 I greater than or equal to 0 I minus minus. Let's make sure this is still working. Very amazing. Now, if not I in used memory, well, that's really what a coincidence. Let's get rid of that. So now we have got one, and we're like, okay, we're going to try and take you, move you somewhere to the left. We're going to find a gap to the left of you. So let's find, what do we want to call you? Because we got two things to pull out of you. Now we'll just call you used. That's really a horrible name. That's okay. As you can see, we have 40 and 2. Yeah, that'll suffice. And now we just need to find the available gaps we can shove this into. So let's put a break statement here. Make our logging a little easier. Yeah, we're just gonna look for the first one. So it would be a find. But I mentioned a sort earlier because we want to make sure we get the leftmost and they're valid. So let's start with the filter. So const freeze equals, it could be any of those keys. So object keys free memory. But let's filter already to ones that are good. These we want to treat these as numbers, so let's map them to a number. And what is this one? This is free size. And we want to make sure now one of them is greater than or equal to the other. Greater than or equal to use size. Get that right? So I have a 2. Okay, I mean that appears to be right. If I swap it, we're gonna get bad. Yeah, this is a whole block of size 2. It cannot go into a slot that is of size 1. That's for part 1 code, which we're not writing. Okay, so this is the correct way around. So now we have a bunch of them. But now what we want to do is get all of the 3s and only consider the ones that we can move into, which are based on their indexes. Like we can move it to any of them realistically, but if we had one with an index of 45, we wouldn't be able to move into that one. So I'm gonna curmudgeon around the data a bit. 3 memory, 3 splice, 0, 50. No, don't delete. There we go. I just shoved a 50 in there so we can test out this filter I'm about to write. I mean, these are all free indexes. I guess I need to add some more data so I can do it. Because we do prioritize left to right, not by slot size. So we need another map here. Filter map. Free size. We still need the size because, as in this example, you might have some free space left. So we'll have to do some math on that. So if we need both, then you know what? Let's go with the same structure. Let's return a location and the size. And the location is going to be pulling from free memory. On size. So we got a lot of locations. We don't like that. We just want the best one, which is the most leftmost one, but not too leftmost. No, it's the most leftmost one. Do we care about looking at these three here, or do we just care to grab the two? Let's be lazy and let's just grab the two. Okay, so now we have both of these, but let's give it a universe in which there was other places we could go. Let's say a size 2 free memory 2 equals an array of 5. Okay, there we go, right? So we have 5 and we have 2. Now, which one of these would we want to pick? I'm trying to think. Would we want to make a multiple attempts? They're whole blocks. The answer is no. We do not want that. If this was part 1, we would, but these are whole blocks, so we don't want multiple attempts. So we just need to want to find the best here. So is the best location 5 or location 2? The best is location 2. So that is a sort. We want to sort by location descending? Yes. A B well, it's B dot lock minus A dot lock. It looks the same. I wanted the leftmost one though, didn't I? I swore that's what I wanted. Is that what I want? Yeah, I want the leftmost. Yeah, if this is wrong, we'll figure it out. Okay, so we have freeze. This is great. Let's get rid of mushy bits here. And I guess we just gotta pull the first one out. So I could be like, hey, well, there's a possibility there's none here. Let's just call it free, and then 0 it, and then free might be undefined. So if no free, continue. We're very sad. Otherwise, we have free and we have used. We're gonna put the one into the other. Now we do need that logic at some point for if the free space is on the right of the used space. Let me try. Look down here. Did. So I just compare the start to the end. Yeah, okay, if I just compare the locations, it should be sufficient. So we've come up with this statement. If free dot lock. No, let's go the other way. Use location is greater than, yeah, to the right of free dot location. Why are you undefined? Because you're weird. Oh, there you go. Don't worry, it's a real thing. Awesome. That means we're good, which means we flip it. Means we're bad. Good. Okay, that's what I wanted to see. So now we have this. What we need to do is, I guess we need to consume it, right? So that involves us setting the used memory at this location. Well, this is a location at this ID to this new location and size. But then there might be some remaining stuff going on, so we'll need to handle that. So right now I have a slot of 3. I'm gonna shove this into. Okay, so let's just start with that. Used I equals new location, new size. Used memory I. Location is, I suppose, it's where this free space is starting, so it's the free location. Size is, well, it's not 3, it's not 2, it's one of them. It's got to be the size. It's got to be the size that I am, so it has to be used size. And then I have to deal with some remaining bits. So cost remaining 3. That's a good name, and that is the free dot size minus used size. Then I'll need to do something, because this might not always be remaining. Put it back. So we have that. We still didn't remove it though, right? Because we're going through things in a map. But we have to get rid of this 2 out of this 3, which is with a pop. So that's easy. So 3 memory with 3 dots, not resize, 3 dot size, which is, yep, and then I just want to pop that. Boop, it's gone. Okay, so we cleaned that up. When we do that, there's a chance we don't have any more. Right, since we're doing 0 on this, we do want to clean up. Because this would explode into an undefined at some point, which our code is not ready for. So to clean that up, we need to we need to check if that's empty now. And if it is, get rid of it. So if length, then we get rid of it. And this is a object, so delete free memory free size. Feels about right. Let's. We don't have any examples because we're running the quick break, but we're running with it. So we have that. We have our remaining memory, which we are not putting back just yet. Excuse me. Our remaining memory, which we are not putting back yet. I think this is the same way we did it up here, because we have a new size, right? And that is called remaining. So still that code, remaining free, It's not memory I, it's, right, because it's a new position. So it was 0, 1, 2, but now it's 2 plus 2. So it's its old free dot size. Well, no, it's free dot location plus used size. I think it's about right. But we gotta make sure I'm doing this totally not a heap logic up here. I gotta put that back. So do keep this nice and sorted. That's important, I think. This is either gonna work or it's gonna not work. So let's find out. Move the brake so we can see some stuff happening. Look at them things, they're doing stuff. Okay, so used memory should all be here. Interesting. So their numbers have changed. Now I don't have a map for this anymore. So how would I rebuild this into a thing I can calculate the checksum from? I guess I'd go for each of these and just rebuild the thing. So for thing and value, I build up a string and I just set their indexes based on that with the size. Okay, so let's memory. Let's just call this an object. We'll redo it by keys later. For const size of object.value to use memory. Then it's for let O equals 0, O less than size, O plus plus. Then it would be raw memory location plus O equals. I did need the keys here. Oh no. Or not the keys, or I guess the IDs. IDs. That worked. Raw memory is like that. Now I think the keys are not going to be nice and ordered for me. Maybe. Oh, I see a gap there. I'm already sad. Okay, let's look this string. Well, there are gaps there, so I can't just do a values on it. I'd have to loop from the beginning to the end and then move things along. Why did those 8s not move? They didn't move in the real one. Why don't those 8s move? You can move right there. Not gonna question my misunderstanding of the straight up logic. String equals, I guess, this. 0, I less than, oh, come on. Less than raw memory dot length. Plus, we're just gonna start shoving things. Okay. Can we just need the largest key here, I guess. Come on, give me object.keys, raw memory, -1 your number. Congratulations, less than or equal to. I remember that from before. Get some deja vu. String plus equal raw memory. Or a dot. See if I can follow this one. Okay, the 0921743. So it looks exactly like what we have in the picture, but I'm kind of paranoid about the picture. I don't understand why these 8s didn't just go into this free slot right here. Gonna hope that's not a problem. Just go steal my old checksum calculation bit. Okay, maybe not this checksum calculation bit. Can I steal this checksum? Please. Of course, why would you want to be useful? Okay, let's at least clean some of this up, maybe make it a little easier for the old machine. Okay, checksum calculation. I got raw memory, I got strings, I got lots of stuff going on here. Nothing wants to be happy. Oh, this is the new code. Yep. Let's not do that just yet. It is really unhappy right now. Okay, woken back up. So checksum calculation. This is the thing that was broken, then I fixed, and then I unbroke. I think it's just this. I just need to iterate over the string. am using this, so then maybe I can use raw memory. I mean, I can't see the number. So test it for, I guess. Oh, might be working. Hmm. Hmm. Suspicious. So it's running. So it's either hit an infinite loop. We'll find out later, I guess, because that is a lot more number crunching than I would have liked. Okay. So kind of getting close to the same position now. We've generated everything in its correct looking position in the example. Correct according to something. And it's not liking it. Well, the example, the input is not liking it. Okay, that's gonna go along and do its thing, I guess. Let me see. Did I goof up any of this? I am seeing that this never gets ran. Maybe we have some logic in here that's preventing that, but I don't remember writing any of that logic to prevent that up there. Okay. Feels like we have not struck gold. If anything, feels like we've struck a while loop. But I've specifically avoided using while loops, so I'm not sure how that happened. Did I make an improper assumption here with the nines? So if I were to just console log use memory and just return here, did I make an assumption that was incorrect with that? Well, show me the other used memory. Oh, geez, it's not. Okay, so that's just. I'll leave it just in case we get somewhere. Okay, yes, that's failing, of course. That does go higher than 9. Yeah, my code's not prepared for that. Hey, um, since I do need to loop from the largest to the smallest and not just where the heck, whatever used memory may be. Cool, cool, cool. Fix that. I'll put that back, not kill our computer. So for const, so it is reverse keys of this. So I object keys. It's reverse, so I gotta use a little bit of something else. I do want it backwards, but I want it numerically backwards, so they gotta be numbers. A, B, descending B minus A. Don't need that conditional. See if it works for our example. It is weird that this didn't. Like, I would have expected it to end quickly, if anything, not run forever, but. Okay, it's working. Let's send it to the new code, which, yeah, you're never gonna solve, I just realized. Stop that. You can go have fun with that. You might get somewhere. You don't know what you're doing. Let's look a little bit into what you're doing. What are you doing? So you got through all of them. What are you doing now? Are you building raw memory? Are you building the string? Like, it doesn't feel like that much. Um, Okay, so you built your raw memory just fine. Are you building the string? You're doing something. I guess we'll call this one C, and this one call this one S. Yes, stop. Okay, you're building a string. Yeah, okay, strings are expensive. I got you, I got you. Don't build a string. I saw you went up to like 100,000 or something. Now you're doing checksum, which is also not really that free of an option. So actually, it appears in my so assuming everything else above is working, this part is what needs to be optimized. My checksum calculation. I forgot how many things we go through. All right, it's a really big number. Okay, so hey, I can target checksum calculation. So yeah, I am unwrapping a lot of it for visualization purposes. I probably don't need to do any of that at all because the checksum ID multiplied by in so location multiplied by ID. I have all that information in here somewhere. Okay, I'll let you go. You'll get there eventually. So instead of doing this, I want to do some other math. Oh, I want all the numbers between two different ranges to be summed up. So if I look at, let's turn off the real, so I can figure this out with my example. Yeah. So we know this is bad. So stop. Ooh, let's stop. We want to loop over the actual stuff. Figure out how to do it from here. So location size. So 002. Oh, this is a horrible example. If location, then let's look at some stuff. Okay, 153. So we have a 1 at location 5, and there are 3 of them. So let's figure out the normal math to get there. Then we'll figure out the cool math to get there. So the checksum for that location 0, 1, 2, 3, 4, 5, 6, 7. So times something, 6 times something, 7 times something, 5, 6, and 7 times the number in here, which is 1. Right? So it's times 1. Then add all these together, so which is 5 plus 6 plus 7. Oh, hey, it's a number. I can't remember which one it was. That was it. Okay. Okay, that means everything is working. All this memory moving tomfoolery, it's doing the job. Woo, that was the main thing. And this checksum calculation was really just going to be, I wasn't thinking it was fast enough, but okay. That that changes a few things. That makes me happy enough to commit this. The refactor, though, is still gonna love that. So let's get this cleaned up to a committal point. And yeah, let's think about all this stuff. It was an attempt, but something wrong here is in the moving logic. Nothing worth recovering. Stop. Clock up. Put that back. All my types are ruined. That's fine. Put that back. We know that still works. Get rid of this stupid import. And let's call that a commit. And then we have the pleasure of optimizing that checksum calculation, at least. Day 9. Woo! I'm getting there. So, where is. Let's get rid of this. And let's get rid of this. Right. Before I get too excited in the refactor, let us go back to the challenge. Try and understand what exactly they're asking with us. So, we have here our input is a disk map. It contains pairs of digits. So all of the even number digits are sizes of files. All of the odd number digits are sizes of free space. So 1, 2, 3, 4, 5 is one long file, 2 free spaces, 3 long file, 4 free spaces, 5 long file. Now, the IDs of the files are the order in which they are seen. So the 0th file has a 0th index, the 1th file has a 1th ID, 2th file has a 2 ID. This can, and at least I did in my code, just take the index of the number, divide it by 2, you get to this number. But it's the index of the file, not the index of the number as seen in this disk map. And then they give you the representation of the big one to validate against. Once you have that structured and data and whatever you like, part 1 is to defragment or basically smush all of the files so that way there are 0 gaps. And the order they want to do it in is leftmost to rightmost, or I guess rightmost to leftmost. Where you have a gap over here, you need to fill it with the rightmost piece of data. Or you have a rightmost piece of data, it needs to go to the leftmost piece of memory. And you continue doing that process for every single individual bit, I guess, in this story until there are no free spaces left. Once you do that, calculate the checksum, which is going through each thing, multiplying the index of the data with the ID of the data. So it's 0 times 0, 1 times 0, 2 times 9, 3 times 9, 4 times 8, and adding up all those numbers. That was the part 1 challenge. Now, the part 2 challenge was the exact thing, but hey, you can't like break up files. Like in this example, the 8 file was broken into 3 different non-contiguous memory chunks. That's illegal. You can't do that. Now you have to make sure that when memory is moved from the right to the left, it's not broken up. Can't break up the family. That's the main difference. There's apparently some other logic I cannot see for the life of me of you're not going further. Because like in this visualization, my brain tells me take the 8, put it in this free slot here. But we don't do that. Or maybe we do, and I'm just not understanding it. Once you do that, you calculate your checksum again. That's the same answer. As for how my code did it, oh, nobody knows. At this point, it feels like nobody knows. But we'll go through it because I do remember somewhat. So the part 1 and part 2 use completely different solutions at this point. As we saw, I had to rewrite part 2 due to the abysmal efficiency of it. Part 1, well, though, it tracked the. Come on, show me my stuff. Okay, turn clock it back on. It's gonna help explain it. So what I went to do is I was like, okay, I want to track every single position of memory that is used. So that's position of memory on the left and what it is used by, the ID on the right. Then also I want to track every single position that is a free memory. I thought this was simplest at the time. I honestly don't know how I'm going to rewrite this, but The way I did that was I went through all the data. I determined if it was a used or a free memory allocation based on the evenness of the current piece of data, grabbed the size from whatever it was, and then for every bit in that size, if it was used, I put it in used memory with a divisor of 2, which was the ID of. That's how you get the ID. I said divide by 2. Otherwise, we're just like, hey, this is where the free memory exists. We increment our position forward like so. Then, while there was free memory, I went through and I got the first one. So, first free, we can see that that one was, the first free slot was 2. So we're looking our slot here, 0, 1, 2. Then I went back and I got the last piece of used memory, which was this 9, by getting the last key of used memory. I did a little bit here where I reassigned whatever is in that last bit of used memory to this new position. Congratulations, the 9 just moved over here. And then, of course, we delete whatever was in its old position. But we just keep doing that until we run out of free memory slots, which is up to this position, because this is the last free memory slot we've ever seen. Unfortunately, this can result in a situation in which there is memory still out here, but it wasn't detected as a free memory slot because during the first lookups of free memory, they didn't exist. So if I were to put this, it should not use memory. Make it somewhat obvious where it is. As you can see, no gaps. Look at all these no gaps, no gaps. And then there's a gap. From 26 to 35, there's a huge gap. So, yeah, I don't know exactly how this worked. Huh. Yeah, there's a reason this is happening. There are 2 6s at the end. Yeah, but one of them's all the way at 36, which is like out here. I don't really know why. But past me figured this out and identified the problem of, hey, now we have some free memory that wasn't initially free memory because here it is. Our free memory only saw up to 35. That was the only free slot. From that point forward, we had a contiguous thing of actual memory, which we could look in here. We see we have 34, and then we have 2 slots at 35. So 35 is basically between the 7 and the 8. It's right here. So we got all of those. Yeah, obviously this code is flawed. I'm not going to explain why it's bad, but it's obviously bad to the point where I had to do 2 passes to get rid of this stuff. Second pass was a bit more manual of, let's find the first free slot in memory, but we have to use used memory now since this thing has stopped being useful. We find the first slot that's not in here. We also remember it for future iteration efficiencies. We get whatever the last slot is, take it out. We do the reassignment as the same thing we did up here, and then we get rid of the old one. So it's the exact same process, but used on a different data structure because this data structure didn't have all the things we needed for some reason. Who knows why? We'll see in the refactor. Then we do the checksum calculation, which, as we have discovered, is not the most efficient, but it goes through all of them and it does that math according to the index multiplied by the ID, which is stored in used memory. Yep, we have the index of everything, and then we have the
ID of the file in that memory. So that's how that part one code works. It's not going to live too long, but part two code, I mean, we just created most of it, but as we saw, we first, instead of going and storing each individual piece of a file, we stored the files as locations and sizes, so a little bit less data to store. We did that by looping through it, using the ID of the file as an index, storing its ID, storing its size. That part doesn't change too much, just different way of structuring the data. What does change is we don't just store all the free memory the same, we store it into buckets that allow us to quickly and more efficiently look up and find the necessary free memory we're looking to store something in. So these are all bucketed by size. So whole free memories that are length of 1, these are their positions. All free memories length of 3, here are their positions. Not only is this more memory efficient to store free memory, ironically, it allows for the O of 1 lookup for free memory slots of certain sizes. We then sort this descendingly because we always want the smallest one at the end for us to pop off in future operations. Speaking of future operations, we then go through every file ID, which is the keys of used memory, and we go through them from right to left or from largest to smallest. So we want to take the 9 and try and move it somewhere over here. So we grab it, we grab all of our free memory. We only look at ones where we can fit it in. So if we're looking at this 8 here, we would never try to fit it in this slot of 3. So if we're looking for free spaces, this would not be considered a free space. Neither would this. This might, and this might, though. So that's what that first filter does. Then we map over, because we do want the locations of them, because we don't want to just fill any slot to the left of us that is free. We want to fill the leftmost slot that is free and available. So we map to get the locations, so that way we can sort ascendingly on them from smallest to largest, and then we grab said smallest. Assuming there is one. If there isn't, then this is very sad. There's no free space to put this. If there is, and unfortunately we just tried to move it to the right. So for example, if we grab this 4 and we're like, we're gonna move you to this free space, that's illegal. We don't want to do that. So this protects us from doing that, which honestly could be done in here, but I didn't. And honestly isn't needed, as you can see, because it never gets ran. But neither here nor there. Once we do get an appropriate block of memory to free space pairing that is valid, can happen, we do the move, which is by saying, hey, that ID, that number, well, now you live at this new location, which is the same size you were before, but your location is now where the free memory started at. We then get rid of that free memory because it's no longer free. And if this was the last free memory of that size, it's like there are no more free memories that are of length 3 after we fill in this 4, we get rid of it because this would explode if you had an empty arrays in there. But there's a possibility in most of these that you didn't fill up all the memory, you filled up some of it. So if there's any remaining free memory, we'll make sure that an array exists for that size, push the new location of this memory here. So it was 3, so we had a new memory of 2 plus original, points us to there, and make sure this is still just sorted the proper way. And the efficient way will be using a min heap or something to that degree. We weren't efficient though. And that's all the memory moving. The checksum math is the exact same from part 1, unfortunately, which is the least efficient thing in the universe, apparently. And the only extra bit here is that we take all of our efficient data and we shove it into the largest object this side, and then we do our old checksum calculation on it. It works, but it's not that efficient. And apparently I broke something. There we go. So it works when you have all the code there. Let's amend that actually. Boop, there we go. Okay, so we have all that there. That's how this code works on the solution. Barely. And like spaghetti, basically. So, now we're going to optimize it a little bit, starting with the checksum calculation of part 2, and then we'll go to the classic refactoring of just making it good in the first place. So, let me continue with the amazing math. So it's 5 times 1 plus 6 times 1 plus 7 times 1. Nothing wants to run anymore. Oh, we have this old code down here. We're not going to need it. It's not useful. Right. So we did that. So what changes here? Location and size. So location determines the starting number. Size determines the ending number. It's the multiplication of it all. And if I were to... So it's 18. 18 times 1. Let me just do bad math real quick. Assume these are by 2. 5 times 2 plus 6 times 2 plus 7 times 2. 36. 18 times 2 is also 36. Okay, so if we can add all 3 of these up into one number and then do the multiplication, then we can just add to the checksum once per this loop. So I just want to add up all these numbers and then multiply them by our I. Okay, so let lock equals 0. Let L equals lock. L less than lock plus size. L plus plus. I need to put this in here to really follow along actually. L. Let's make this a little easier for myself. If I triple equals 1. Okay, 5, 6, and 7. We did it. Lock total plus equal L. Now we have a lock total of 18. We do, which means checksum is 18 times I, which I is a thing, but I think that'll work. Checksum plus equal lock total, not location storage, times I. 18. Well, it'd help if it ran on the rest of the code. Okay, it doesn't like any of this code now. What have I done? Okay, it likes it. It's running. So I believe this is more efficient. I don't think it's the efficientest. Just save. We're adding up, what is it? Continuous sum of numbers from one range to another range. There's a trick for this. Ooh, I don't need it though. It's good enough. Hey. Okay. This does what I want it to do. I know there's a way of doing this. I have to Google it. Numbers from start to end. What's it called though? Is it literally just called the sum of integers formula? That okay. I'm not gonna remember this, but okay. So let's figure out cost total. Let's get rid of this code. My 5, 6, and 7. So we'll see where this goes. So end equals location plus size. Start equals location. inclusive or exclusive? Ooh, it looks like it's being inclusive. So do I need a -1 on these? Hey, there it is. Eh, It's kind of, it kind of looks a little gross. I'm gonna throw that into a function. Function some int start end. Oh, I'm just gonna take the old algorithm. That will be good. Oop. There we go. At least it's somewhat more readable. It's like, what's this weird math? Oh, you're doing weird math. Cool. So sum of integers from location to location plus size -1, because inclusivity versus exclusivity. We love it. Okay, and yeah, JavaScript's cool with it. TypeScript's not. We'll do that. Okay, this is checksum calculation doing its job and so fast. Also, I wonder if that's what's slow about part one. Let's the data structure in part one is trash. Okay, that's sufficient. So that does the trick. What do I want to do now in refactoring? I'd love if I can refactor 1 and 2 into a single function. They're so different though. The thing is, for 1, let me just look at this. Yeah, the structure is literally inverted. Okay, yes, there's opportunity here to do that. I will clean it up where possible. I'm not guaranteeing a full freaking refactor though. Okay, so let's see what we have. I like this checksum calculations, doing its job. Yeah, optimization with heaps and stuff. We're fine here. Yeah, we need that variable. Assign. We can put a new one there for cleanup. Oh yeah, this can be shoved into our filter of some degree. Let me go for that. Um, this thing's getting pretty long. Let's give us some horizontal real estate. So yeah, it'll have to be after this map. So then we can say that filter, so free location. There we go. So that means free location. And I'm inverting this, and then I'm inverting it into a statement. So the inversion of this is this, which means if I invert the inversion, it's free location less than used location. Oh, it's not free location, it's location. Did it do it? It did it. Hey, chuck it all in the filter. Awesome. And then sort and then grab the first one. Yeah, can we do this filter? We need the location. We don't have it until we do that filter, which put you on your own line. Yeah, it's easier, I think, to build the memory, to build the thing and then do that instead of just access it, because we'll need to double access it here and for this. Okay, I like it. All of them used. Yep, we do this. Free. Yep, we do that. Pretty happy with this. This is a little chaotic. Let's rename this to location. Boom, get to save that. Do we use this a lot? We use it once. Let's not do it once. Size, we use that everywhere. Let's keep doing that. Yeah, honestly, I'm pretty happy with this. So we have the first part where we get all our memory, second part we move stuff around, third part do the checksum bits. Yeah, pretty happy. This part one though, oof. Let's at least get name and consistency correct. We can do that. I'm seeing a similar structure here, but the data structure, the similar process, the data structure though, absolutely trash, and we don't use this, so goodbye. Oh yeah, we use this for our pushes. Okay, this is gross. Let's at least try and make this somewhat better. If you're this, then you're doing this. Oh boy, what have I done? There you go. Else you're doing a weird loop. Both of them have the location incrementing, but we use the location in both. No, put it back, put it back. We were doing stuff. There was important stuff there. My bad. And we do that because we need location to persist outside the loop. Can't persist inside the loop because it changes based on size. Yeah. Doesn't mean we're using the loop to do two things: assign and move this thing forward. It's fine. It's gross. Okay, this one, I actually like this. We can optimize this a bit. Move used keys up here. Just be used keys, which is a pop, really. Boop. And then we do that, and then, yeah. Some things are type angry. Nope, I broke it. When did I break it? Did I just break it, or was it always broken? That broke it? Because we changed that. Well, it would help if I put a freaking method on this. Oh, we're also adding this to our keys, I guess. Yeah. Okay, so what if I just manually do that? Use keys dot push first free, and then I'll have to sort the thing, won't I? Yeah, I will. Okay, this is becoming more effort than it's worth. Was it worth it? I don't know. I don't think it just got blazingly fast. Yeah, that did make it blazingly fast. We're not gonna do that. Just the extra key call, well, which is more expensive? Recalculating or resorting? I think this is probably the more least expensive one. So use keys to do that. So that's the work. This is the work to support the work. What are you? You're an array of strings. Oh, I just pushed a number into there. Are they numbers? They are numbers. Mm, fine, you're a number now. Or you're a string now. Alright, you can't sort because keys. And now your numbers now. Boy, it's really not looking worth it at this point. Let's not do it. There we go. Good enough. We'll pay the price. It's not that bad. Okay, we get the things, we swap the things, we're good. Yeah, as inefficient as both of these are relatively straightforward. I think I tackled some of the inefficiencies last time. Yeah, with that, I'm pretty happy. I know it's not the most efficient, and there is definitely room for improvements, but I'm satisfied with it as is. It's readable, it's followable. That's the number one primary thing. Yeah, TypeScript, shut up. I did the Lucy comparison. I'm good. I figured out that comparison optimization, which I'm really happy about. Optimize. A little bit. There we go. This will generate the right number, I know it. But that is as far as I will be taking Advent of Code Day 9. Bit of a tricky one. The math got to me, but made it there in the end. It's a pleasure as always.